So we will start today to solve problems on chapter 14. Then I will introduce the calculation part of chapter 15 to you, and we will do problems next time on it. Okay? So for to start with problem on chapter 14, we have a stainless steel has a flow curve with strength coefficient of 1200 megapascal and strain hardening exponent of zero point 0.4. A tensile test specimen with gauge length of 100 millimeter is stretched to a length of 145 millimeters. Determine the flow stress and average flow stress that the metal experience at this strain. So first, let us see what are the equations we should use. First, they gave us the strength coefficient and the strain hardening exponent of stainless steel. So we can relate then sigma and epsilon, of course the true values, by sigma equal to k times epsilon to the power n. Okay? This will allow us to calculate, if we know what the value of epsilon, we can determine the flow stress at the required point. Now, to get epsilon, they gave us the initial length is 100 millimeter, and it is stretched to a length of 145 millimeter. So the true strength epsilon can be calculated as ln of L over L0. So here, all we have to do is to replace L by 145, okay, and L0 by 100, so we can get the value of epsilon 2. Once we get the value of epsilon 2, we can replace back into our formula. So we replace epsilon here, knowing the values of n and k, we get the value of sigma. This will correspond to the flow stress. Now, they asked us also to determine the average flow stress experienced by the metal when reaching the strain. So you know that in general, we have that the strain hardening curve will start from yield point, okay? And at yield point, the value of epsilon is negligible, nearly equal to 0. This is why we consider that once the strain hardening zone will start, nearly here epsilon is very close to 0. So we can, for approximation and average stress calculation, we can consider that the starting point is characterized by nearly epsilon 0, and the final point is the one for which we are performing calculation. So we want to find the average flow stress between 0 and epsilon. When you want to average a function, okay, what can you do? So here you want to average function sigma between 0 and epsilon. So you can perform that sigma average. We are noting it as flow stress here. So we denoted it as YF. So it's the average stress of flow stress. So YF average is equal to integral of sigma d epsilon. So I will integrate this function and I will divide by delta epsilon. This will give me the average value. Okay. Now I will integrate here from the start of the strain hardening curve to my point of interest. So here from 0 to epsilon. And since I consider that epsilon beginning is nearly 0, then delta epsilon is equal to, I can replace delta epsilon just by epsilon, because it's epsilon minus 0, equals to, since sigma is given in the strain hardening zone function of epsilon, sigma is k times epsilon to the power n, then when integrating this formula, I get k epsilon to the power n plus 1 over n plus 1 times epsilon over n plus 1 times epsilon. And by simplifying epsilon, okay, you have epsilon n plus 1 over epsilon. If you simplify it, you just get that the average flow stress is given by k epsilon n over n plus 1. This formula is included in chapter 14, okay? So here I just derived it for you to know from where we got this formula, but you can directly apply it. So now, since we have everything, we have K, we have epsilon at the final state, we have N, then we can calculate the average flow stress experienced by the map. Any question
Okay.
on this?
Yes.
Yeah.
دكتور بس لسه اعتبرنا ابسلون هي equal to 0 هو الوحدة.
لانه at yield الابسلون at which yield start عاده بتكون كثير صغيره. اوكي يعني compared to the final value of epsilon it is negligible. This is why فيك تعتبرها nearly zero. اوكي يعني اذا بترجع لاكزامبلز اخذناهم بتشابتر chapter 3 جرب خد الابسلون at yield وابسلون final. You will see that epsilon yield is very small compared to epsilon final. So you can do this assumption of neglecting it.
Okay.
Yeah? يعني هو منه zero بس it's very close to zero compared يعني because it's small compared to final epsilon so we can neglect. Okay. وإلا إذا بدك تكون very accurate you should calculate what is epsilon yield and then you integrate from epsilon yield to epsilon final. Okay. So here we can see the details of calculation. We have epsilon yielding L over L0. The flow stress is calculated by K epsilon to the power N. And then the average flow stress is calculated from K epsilon N over N plus 1. And of course, you will see that the average flow stress will be lower than the maximum stress. And it will be between the stress of yield stress and flow stress at the point of entry. Another problem, a tensile test is performed to determine the strength constant C and the strain rate sensitivity exponent M for a certain method. The temperature at which the test is performed is 500 degrees. At a rate of 12 per second, the stress is measured to be 160 megapascal. And at a strain rate of 250 per second, the stress is equal to 300 megapascal. Determine the value of C and M in the strain rate sensitivity equation. Then, if the temperature were 600 degrees, what changes would you expect in values of C and M? So, in this chapter, chapter 14, we have seen that an additional effect is the effect of strain rate on the stress. Okay, so we have a certain sensitivity between stress and strain rate, which is related to the strain rate is defined as the velocity approaching the metal to its height. So here, if you have a certain, for example, a compression operation, then the plates are compressing your specimen. The height will be reduced. At each instant, the strain rate is the velocity of the approaching. So if I draw the figure, let's say you have here a specimen between two plates. You can have it. You can have a compression test or a tension test. So if you have a tension test, let's say, at any instant, if I fix the velocity, what will happen to the strain rate? So here, the strain rate is defined as the velocity. In general, we fixed one of the plates and we move the other. Okay. So for example, here, let's say I am moving down this plate. Okay, for example. Okay. Then I can calculate at each instant the strain rate as the value of the height of the specimen, V over H. So if this is V and this is H, the strain rate is calculated as V over H. Okay. In general, for example, in a certain operation, we might vary the velocity. So if you want to increase the strain rate, we should increase the velocity of displacement during the tensile test. Okay. So here, what we are giving us for a fixed temperature of 500 degrees, when doing an experiment, we have for a strain rate of 12 per second, the stress is 160 megapascal. And for when reaching a strain rate of 250 per second, the stress is 300 megapascal. So this will allow us to determine the relation between stress and strain rate. Okay, the stress can be calculated as sigma. So it's similar to the strain hardening equation. So sigma is equal to a certain constant C for a fixed temperature times the strain rate epsilon dot to the power the coefficient m. Okay. Now, at room temperature in general, okay, the strain rate will not affect widely the stress. So m is close to 0 for for ambient temperatures. But as the temperature increase, the strain rate will affect more the value of stress. This is what we call strain rate sensitivity. So the sensitivity to strain rate will increase when increasing the temperature. Okay. So for example, if you plot on a log-log scale the variation of stress with strain rate, you have for room temperature, you nearly have a straight line, no effect, no measurable effect. And as you increase the temperature, what will happen is that the slope of your curve will increase. So the sensitivity to strain will increase, but the value of stress will decrease. Why? Because we know that increasing temperature will reduce the stress because your metal can be easily, and you can deform it easily when you heat. Okay, this is why when you heat, the value of C will be reduced while the value of M will be increased because C will be reduced since it will be easier to deform your metal, but M will increase since the sensitivity to strain rate will increase. Okay. Now, first they gave us a fixed temperature. So for a fixed temperature, we have constant values for C and M, and to determine C and M, we just need 2 points on the graph. So it's similar to the calculation of the strain hardening exponent and strength coefficient. Okay, so here to calculate C and M, we need to write 2 equations. Each point will give us 1 equation. So for example, from the first point, I can write that what is the value of sigma? For the first point, sigma is 160 megapascal equals to the constant C times the strain rate, okay, to the power. So the strain rate is 12. So times 12 to the power m. Okay, this is equation number 1. Now using the second point, I will get my second equation. So 300 is equal to the constant C times 250 to the power m. This is equation number 2. Okay, and here, or of course, the solution of the system, you can do it by several methods. The easiest way is to linearize both. And you divide first the equation 2 by 1, then you do ln for both sides, you get the value of m. And once you get m, you replace in one of the 2 equations to get the value of C. Okay. Now, if the temperature was increased to 600 degrees, what changes would you expect in the values of C and M? So as we discussed together, with increase of temperature, C is reduced and M is increased. Okay. So let us see together the solution. So first here, we set the 2 equations. Here just for solution, they instead of dividing, they linearized both equations by doing ln for the sides, and then they solved for by eliminating ln of C. They solved for m, and once they got m, you can replace or in equation 1 or in equation 2. Since when you have ln, you might have some errors in calculation. They replaced m in the 2 equations. So they get 2 values of C, but the values are very close. So you can take an average value if you want, or you can just replace in one of the 2 equations because the error is small between the 2 values. And just for the unit, pay attention for the unit, okay? The unit of C here will be megapascal second, okay? So C unit is different here than unit of sigma because the rate epsilon dot is 1/second. So C should have as unit megapascal times second in order in total to have the unit for sigma of megapascal. Okay. Now, in part B, if the temperature, as we said, if the temperature is increased, the strength constant would decrease and the strain rate sensitivity will increase. Now, another problem on chapter 14. A work part with starting height of 100 millimeter and diameter of 55 millimeter is compressed to a final height of 50 millimeter. So here we have like a compression test. Okay, so we have two plates and we have the specimen in between, and we are doing compression effect. So here what will happen is that if we fix the velocity of motion of the plate, with time the height will be reduced and the strain rate will increase, because by definition the strain rate epsilon dot is given by V/H. Okay, and the value of V is it can be in meter or millimeter per second, so depending on the problem. Here, for example, if they give the velocity in millimeter per second, then you should provide the height in the equation in millimeter in order for units to simplify and get at the end the strain rate in 1/second. Okay, so here a work part with starting height of 100 millimeter and diameter of 55 is compressed to a final height of 50. During the deformation, the relative speed of the plates and the compressing part is 200 millimeter per second. Determine the strain rate at for H equal to 100 millimeter, H equal to 75, and H equal to 51. So you can expect that as H will decrease, having a constant value of V, then the strain rate will increase. So when you perform a tensile or compression test, here in a compression test, if you fix the velocity, the strain rate will increase with time. If you do a tensile test and you fix the velocity, then the strain rate will be reduced with time. So if you wish to increase the strain rate, you should increase your velocity. Okay? So here we will see that we will calculate the strain rate for different values of H, and we will deduce the profile expected that with decreased H, epsilon dot will increase. So all we have to do is just to apply V/H and just pay attention for units. So here already the units are not confusing, but if they provide H in meter, make sure to convert to 1 unit both. Okay. So here, by application of the formula, I can calculate the strain rate at different heights, and it will be clear that as I decrease the height, the strain rate will increase. Okay, so as you can see, the formulas of chapter 14 are very simple. You have just numerical applications. Now we will go over a little bit more complex calculations in chapter 15. So we will introduce together the calculation part in chapter 15 so that we can do next time problems on this chapter. You have on Blackboard already this folder is posted, processes equations. It is posted in the problem section. Okay, in this document you can see formulas from chapter 15 and 16. Okay, now we will cover just the part of chapter 15 to do problems on it on Wednesday, and after this, when we are done with chapter 15, I will continue the second part of equations, which is for chapter 16. So in this chapter, first we will go over equations for the case of flat rolling. To remember what is flat rolling that you covered in the material, in flat rolling, we have two rollings rotating at opposite angular velocities in order to reduce the thickness of a slab passing through or a plate passing through the rolls. Okay? So the concept is very simple. You have a certain plate, rectangular plate of initial thickness T0, and you wish to reduce this thickness. So you pass it through this gap between two rolls. Now the rolls are rotating at opposite angular velocities. So as you can see, for example, here, you have this roll rotating in the counterclockwise direction, and this roll rotating in the clockwise direction. You have that the linear velocity of both is equal. The linear velocity of the rolls VR is calculated as the radius of the rolls R times omega, where omega is called angular velocity, and VR is called linear roll velocity. Okay. Now, what will happen is that because of contact between the rolls and the plate, as you can see here, you have a contact area. You will have a certain pressure forces exerted from the roll on the plate, and due to these pressure forces, you will create a certain friction force in the tangent direction between the roll and the plate, and this friction force will allow in total the plate to move forward, and we will see that the final velocity will be higher than the initial velocity while the thickness will be reduced. So now in this session we will see how to relate these variables together and how to compute the variation of thickness when a plate will go through a certain through a rolling system. Okay, so to start with, we will do an analysis on flat rolling. So flat rolling, which is illustrated in the figure, involves the rolling of slabs, strips, sheets, and plates, or in general, any work part of rectangular cross-section in which the width is greater than the thickness. In flat rolling, the work is squeezed between two rolls so that its thickness is reduced by a certain amount, which is called the draft. The draft is calculated by the following formula as the final thickness is the starting thickness minus the final thickness. Okay, so this is if you want the total amount of reduction of the thickness when going through the rolling operation. Now, in case D is in millimeter, then the starting and final thickness should be provided in millimeter. You can also work with English units. For example, you can provide it in inch. So in case D is an inch, also I will use inch for the thickness. Now, another parameter that is used to define flat rolling is reduction. Reduction is the ratio of the draft over the original thickness. Okay, and in case you have a series of rolling operation, because sometimes you cannot reduce the thickness in one pass. You need to do multiple passes of your metal, of your plate between rolls in order to achieve the final reduction. Because we will see together that for a certain rolling setup, you have a maximum draft per pass. In each pass, for example, let's say if you calculate that each pass will allow you to do 1 millimeter reduction. Okay, if you desire to do 10 millimeter reduction in draft, then the total draft will be achieved by doing 10 different passes through the rolling. So I should have 10 passes to achieve the total draft required. So when we talk about reduction, we talk about the total draft over the initial thickness. Okay, so when a series of rolling operations are used, reduction is taken as the sum of the drafts divided by the original thickness. In addition to thickness reduction, rolling usually increases work width because you have the thicknesses reduced, the width will increase. This is called spreading, and it tends to be most pronounced with low width to thickness ratios and low coefficient of friction. Conservation of matter is preserved, so the volume of metal exiting the rolls equals to the volume entering. So from mass conservation, since we have equal density, okay, we can apply conservation of volume. So the volume entering the rollers will be equal to the volume exiting the rollers. This will allow us to write this the following example.
وين في سبراي؟
Please guys. حدا عم يحكي. Please can you mute your microphones if you are not asking questions, please. So here, this relation will give me a relation between the entering parameter and the exiting parameter. So T represents the thickness of the plate, W is the width, and L is the length. So from volume conservation, T0, W0, L0 is equal to T final, W final, L final. Okay? And if we want to write a rate equation, so if we derive this equation with respect to time, we know that the velocity of the plate going through the rolls is the derivative of L with respect to T. So by deriving this relation with respect to time, we will get a relation involving velocities. Okay? So here in this equation, W0 and WF represent the work width before and after passing through rolls. L0 and LF represent the length before and after, and the same for the thickness T0 and T final. So now if we derive this relation, we can get a relation between V0 and V final, which is the velocity before going through the rolls of the plate and the velocity after going through the rolls. So T0, W0, V0 is equal to T final, W final, V final. Since when deriving here with respect to time, d by dt, the derivative of length is velocity. So dl by dt is equal to v. Okay. So you get in this way a relation for the volumetric flow rate. So this is if you want, called conservation of volumetric flow rate through the rolling system. So conservation of volumetric flow rate. Okay. Now, the rolls contact the work along an arc defined by the angle theta. So if we look at our figure here, the contact length between the rollers and the work is this arc of circle here. Okay, this one. This is called the contact length. And if you want to find the contact area, if I draw, I should multiply L by the width of the work part. Because as you can see, if I represent the 3D view of it, okay, so I have a certain width here. Then I should, to find the total contact area, I will multiply the contact length by the width. I get the contact area between the rolls and the plate. Okay, so I have here from each side, I have the same contact area. And the contact area is very important to know because it will allow me to calculate the average force exerted by the rolls on the work part, as we will see together. Now, what will happen is that here, first you have an initial velocity V0, okay? As you go over the rolls, the final velocity will be much higher than V0. So if you want, what will happen is that VR, which is the linear velocity of your rolls, is between V0 and V. So when passing through the rolls, the velocity of your plate will increase and it will pass at a certain point by VR. So the point of contact with VR, for which the velocity VR equal to the velocity of the work part, is called no slipping point. So when we say no slipping, this means there is no relative velocity between the two. And the two parts will not be sliding at this point. But before this point, we have, of course, a sliding. And after this point, we have sliding between the two parts. But the difference is that before the no slipping point, VR is higher than V0. This means that the net friction, the friction of the roller on the work part, the action of it will be in this direction, which is opposing the relative velocity between them. Okay? So the roll will tend to move the part in this way, in a way tangent to the circle. Okay? So if you calculate the resulting friction on this part is positive in this direction. Now, after the non-slipping point, what will happen is that after the non-slipping point, the opposite will take place. The work part will have a higher velocity than the roll, and then in this case, the roll will have an opposite action on it. It will try to reduce its velocity, if you want. Okay, So it will have a friction opposing motion. But for me, I am interested in the net friction. The net friction over the whole contact area will be pushing forward in this direction, and therefore this will allow my part to move in this direction, to pass through the rods. Okay. Now, this will be explained here. So the rolls contact the work along an arc defined by the angle theta. Each roll has a radius r, and its rotational speed gives it a surface velocity vr. This velocity is greater than the entering speed of the work and less than its exiting speed. Since the metal flow is continuous, there is a gradual change in velocity of the work between the rolls. However, there is one point along the arc where work velocity equals the roll velocity. This is called the no-slip point, also known as neutral point. On either side of this point, slipping and friction occur between the roll and work. The amount of slip between the rolls and the work can be measured by the means of the forward slip, a term used in rolling that is defined by, so the forward slip, which will lead to motion of the plate from one side to the others, passing the rolls, is V final minus VR over VR. So in general, the forward slip is characteristic of the rolling operation. So they can give it to me, and I can in this way relate V final to linear velocity of the rolls, where S is the forward slip, it's without unit. VF is the final exiting work velocity, in meter per second in SI unit, or in feet per second or inch per second in English units. And VR is the roll speed. Now, if I want to compute the average force acting on my contact area, first I can calculate the true strain experienced by the work in rolling process, which is based on the variation of thickness. So here, since it's a squeezing operation, we have reduction of thickness. So we will use epsilon compression. So the absolute value of epsilon in compression is ln of T0 over Tf. And the true strain can be used to determine the average flow stress to which applied on the work material. So we can then calculate the average flow stress from the previous chapter from K epsilon n over 1 plus n. The average flow stress will be used to compute the force and power used in rolling, as you will see together now. Now, whenever I have this force, as we said, this force is normal to the contact area. So you have the contact area, the resultant force is normal to it. And if you have any contact between a surface and an object, okay, whenever you have a relative motion between them, you can have what is called friction force between the surfaces, okay? And the friction force is related to the normal reaction between them. So here, if I have a normal, okay, then I can calculate friction from the friction coefficient mu times the normal. So here, by computation of the force F, I can determine the friction force, okay, because the friction force is related to the normal action, okay? So the average flow stress, the friction in rolling occurs with a certain coefficient of friction, and the compression force of the rolls multiplied by the coefficient friction will result in a friction force between the rolls and the work. Now, as we said before, on the entrance side of the no-slip point, friction force is in one direction, and on the other side, it is in the opposite direction. However, the two forces are not equal. The friction force on the entrance side is greater, so that the net force pulls the work through the rolls. If this were not the case, rolling would not be possible. There is a limit to the maximum possible draft that can be accomplished in flat rolling with a given coefficient of friction defined by. So as we said, you have a limit for the maximum draft you can perform in one pass. The maximum draft is related to the radius of the roll and to the friction coefficient between the two surfaces. So it's m squared times r, where d maximum represents the maximum draft, and here per pass, okay? So this is per pass, of course. So if you want to have a higher draft, you should do multiple passes. You should pass your work part several times through the rolls. Mu represents the coefficient of mu or m. Okay, this is the same. It's the coefficient of friction between the two surfaces. And r is the roll radius in millimeter or inch. The equation indicates that if friction were zero, draft would be zero. So no possible operation without friction between the surfaces. Any question on this? Okay. Now, given a coefficient of friction sufficient to perform the rolling operation, the roll force F required to maintain separation between the two rolls can be computed by integrating the unit roll pressure over the roll work contact area. This is expressed by F equals to integral PWDL. What do we mean by this? Here, look, we have a certain contact area between the work part and the roll, okay? And this contact area is L times the width of the work part. Now, you know that to calculate a force, you need to multiply the pressure or stress times the area. So here at each point, you have a certain pressure of the rolls acting on your work force. So if you want to do the integration procedure, the force can be computed as integral PdA, where P is the pressure or an elementary area, and dA is the area to consider. Here, since the pressure is varying along this direction, then along the width, you don't have variation in pressure. This is why we can say that dA is W, which is the width times dL. And then since I consider a constant value of W, I can take W outside and say that the pressure is varying only along L. So I will integrate over L the pressure value. Now, instead of doing integration, I might use an easier procedure, which is the calculation of an average force. Okay, so we can say that F can be calculated as an average stress, okay, sigma average, times the area of application. The area of application is W times L, and sigma average is calculated as the average flow stress value that we have seen together. So we can use the average flow stress definition to get an approximation